everything you've been told about falling into a black hole is probably a little wrong. That you'd be crushed the instant you touched it. That you'd freeze at the edge forever. That it's a cosmic drain that sucks everything in. The truth is stranger and more beautiful. So let's actually do it. Let's fall in. But we're going to fall twice. Once into a black hole 10 times the mass of the Sun, packed into a sphere the size of a city. And once into the monster at the center of our galaxy, Sagittarius A star, 4 million times the mass of the Sun. And here is the first thing almost nobody expects. The giant one, the 4 million solar mass monster, is the safe one. The gentle one. Fall into the small black hole and you die screaming before you ever reach it. Fall into the giant and you cross the point of no return without feeling a thing. This isn't a paradox, and it isn't science fiction. It's a straight consequence of Einstein's gravity, and by the end, you'll understand exactly why. First, forget the idea of a black hole as an object. It isn't a thing sitting in space. It's a region, a place where gravity is so extreme that not even light moves fast enough to escape. There's one number that defines it, and it's surprisingly simple. It's called the Schwarzschild radius, 2 times the mass times gravity's constant divided by the speed of light squared. What it gives you is the size of the point of no return, the event horizon. And the remarkable thing is how the size scales. Take our Sun. To turn it into a black hole, you'd crush its entire mass into a ball just 3 kilometers across. Our 10 solar mass hole, about 30 kilometers, the size of a city. But Sagittarius A star, with 4 million solar masses, has an event horizon 12 million kilometers wide, roughly a fifth of the distance from the Sun to Mercury. That's the range. A black hole's horizon can be the size of a town or the size of a solar system, depending only on how much you feed it. And one myth to kill right now: a black hole is not a vacuum cleaner. Swap the Sun for a black hole of the exact same mass, and Earth's orbit wouldn't change at all. From a distance, gravity doesn't care whether the mass is a star or a hole. You have to get close for the strangeness to begin. So we begin our fall. From far away, an observer watching you drop toward the horizon sees something eerie. Your clock begins to run slow. Your radio signals stretch. Your color shifts from white toward red, toward infrared, toward invisible. To them, you are slowing down. Hold that thought. It matters later. As you fall closer, you reach a strange shell of space called the Photon sphere at 1.5 times the horizon radius. Here, gravity bends the path of light so severely that light itself can orbit the black hole. Photons circle it like moons. And that means if you looked out to the side, you might see the back of your own head, light that left you, wrapped all the way around the hole and came back to your eyes. This is not a trick of the imagination. It's a filmable prediction of general relativity, and it's the last real landmark before the edge. Beyond here, the two falls, the small hole and the giant, stop being the same story. Here's where they split. Gravity pulls harder on the parts of you that are closer to the hole. Your feet, falling first, get pulled harder than your head. Stretch that difference far enough and it tears you lengthwise while squeezing you from the sides, physicists call it, with a straight-faced spaghettification. Now, how strong that stretching gets at the event horizon depends on the mass, and it depends on it in a way that flips everything. The tidal force at the horizon scales as 1 over the mass squared. Square it. That means a black hole 1,000,000 times heavier has a horizon 1,000,000,000,000 times gentler. For our small 10 solar mass hole, the stretching becomes lethal thousands of kilometers out. You are pulled into a thin stream of matter and destroyed long before you reach the horizon. You never even get to cross it. But at Sagittarius A star, the horizon is so vast and the curvature so gradual that the tidal force there is feebler than the tug you feel standing on Earth. You would sail across the point of no return completely intact, calm, whole, feeling absolutely nothing. Same physics. opposite fate. And it all comes down to that 1 over mass squared. So let's take the gentle fall, the supermassive one, and actually cross the horizon. And now we get the strangest split of all, what you experience versus what everyone else sees. To the distant observer, you never cross at all. Your image slows, reddens, dims and freezes, hovering at the edge, fading toward black but never quite winking out. To them, you are trapped at the horizon for eternity. But that is only an image, light struggling out against gravity, stretched and delayed until it can't reach them anymore. It is not what happens to you. From inside your own suit, there is no wall, no barrier, no moment of crossing. Your clock ticks normally. You pass the event horizon in ordinary finite time, and for a hole this big, you might not even be able to tell the instant you did it. The horizon isn't a surface you hit. It's a line drawn in the geometry of space, a boundary that means one thing only: from here, no signal you send will ever climb back out. Once you're across, the universe rewrites its own rules. Outside the black hole, you can move any direction in space, but you're dragged forward through time. You can't stop the clock. Inside the horizon, those roles swap. The center, the singularity, stops being a place ahead of you in space. It becomes a moment ahead of you in time. Reaching it is no longer a matter of direction. It's as unavoidable as tomorrow. You cannot steer around it any more than you can steer around next Tuesday. And here's the cruel twist. If you fired your engines, burning everything you had to thrust away from the center, you would only reach it sooner. Struggling costs you time. The most life you can squeeze out of your final moments comes from doing nothing at all. You can still see the outside universe. Light keeps falling in alongside you, but nothing you do, no message you send, will ever leave. How long do you have? Again, it comes down to mass, but now it flips back. The time from crossing the horizon to reaching the center scales with the size of the hole. For our small 10 solar mass black hole, if you had somehow survived to cross it, you'd have about 1/10 of a millisecond, less than the blink of a blink. But inside Sagittarius A star, you'd have tens of seconds. Whole seconds of lived experience, falling through the dark interior of a black hole, watching the warped sky shrink behind you. And in those final moments, the reprieve ends. The tidal forces that were so gentle at the horizon finally begin to climb, and climb, until even here, in the gentlest giant, spaghettification becomes inescapable. Everything that is you is drawn toward a single point. And then we reach the edge of what physics can tell us. At the center, Einstein's equations give an answer, and the answer is infinity. Infinite density, infinite curvature, a point where space and time themselves pinch out of existence. But here is the honest truth, the one you should hold on to over every dramatic image you've ever seen, that infinity is not a discovery. It's a failure. It's the mathematics of general relativity raising its hand and saying, "I don't work here anymore." Whenever a theory predicts infinity, it isn't revealing reality, it's revealing its own limits. To know what's truly at the center of a black hole, we would need a theory that unites gravity with quantum mechanics, a theory of quantum gravity. And we don't have one. Not yet. So when someone tells you exactly what a singularity is, they are guessing. The real answer, the scientific answer, is the hardest one to say out loud: we do not know. And that not knowing is not a weakness of the story. It's the frontier. Now step back, all the way outside, and watch the black hole itself over unimaginable time. Because black holes are not eternal. In 1974, Stephen Hawking showed that the churn of quantum fields at the very edge of the horizon should make a black hole glow, faintly, thermally, leaking energy into space. We call it Hawking radiation. And the temperature scales as 1 over the mass, which means the biggest black holes are the coldest. A black hole the mass of the Sun would glow at around 60 billionths of a degree above absolute zero, colder than deep space itself. And that leads to something wonderful and strange. Right now, real black holes are not shrinking. They're growing, swallowing more warmth from the leftover glow of the Big Bang than they radiate away. Only in the far, far future, once the universe has expanded and cooled below even their whisper of heat, will they finally begin to evaporate. And when they do, it is slow beyond comprehension. A solar mass hole would take something like 10 to the 67th power years to disappear. The universe is 14 billion years old. Black holes are, for all practical purposes, the last things that will ever exist. But Hawking's discovery left a wound in physics that still hasn't healed. If a black hole slowly radiates away into featureless heat, then everything that ever fell in, every star, every signal, every trace of you, is gone. Erased. And quantum mechanics says that's forbidden. Information cannot simply vanish from the universe. This is the black hole information paradox, and for 50 years the sharpest minds in physics have fought over it. Some propose that the infalling traveler hits a wall of fire at the horizon, after all, a firewall, burning out the moment they cross. Others insist that nothing special happens at the edge, exactly as Einstein demands, and that the information escapes in ways we're only beginning to decode. Recent work hints the information does survive. But there is no final answer. Not yet. And that's the honest place to end. A black hole is where our two greatest theories of reality, gravity and the quantum, collide and contradict each other. Fall in, and you pass through the best understood physics in science, straight into its deepest unsolved mystery. The edge of a black hole is also the edge of what we know. This has been Science Untold.